Okay, hello guys, welcome to solving another problem. In this session I want to solve some examples and talk to you about that. Okay, so let's do it. Okay, this example is example 10.4 from chapter 10, which is related to heat exchangers. Okay, but let me as usual introduce the reference that we are working on that. Okay, this is a heat transfer 10th edition of that from Professor J.P. Holman. First chapter is introduction, second is about second and third about conduction. Chapter 4 is about unsteady or transient steady state conduction. Chapter 4 is about convection, and chapter 6 is about empirical and practical relation for forced convection, and natural convection system is discussed in chapter 7, and chapter 8 about radiation. Okay, and chapter 9 about condensation and boiling heat transfer, and finally chapter 10 is talking about heat exchangers. Let me go to page 536, which is example 10.4 in here. Okay, let us read it together. Water at the rate of 68 kg per minute is heated from 35 degrees Celsius to 75 degrees Celsius by an oil having a specific heat of 1.9 kJ per kilogram degree centigrade, and the fluids are used in a counterflow double pipe heat exchangers, and the oil enters the exchangers at 110 degrees Celsius and leave at 75 degrees Celsius. Okay, so the overall heat transfer coefficient is 320 watt per meter square degree Celsius. We should calculate the heat exchanger area. Okay, we should calculate A. We're gonna talk about that. Okay, then let's do it. Okay, let me set it. Okay, if we want to we should draw the diagram like figure 10.7b, because as it said, the flow is counter current flow. It means one of the fluids go from left to right and another from right to left. Okay, for example, hot and cold. The direction of these two fluids are different, so we should use the second diagram. Okay, but in difference, because we want to, we should calculate delta Tm. Okay, so we should change the cross section 1 to 2. Okay, Then let me first write the formula to calculate this example. Okay, the formula would be that Q equals UA delta Tm. But we don't have delta Tm. We should find it and find A2, but we have U. What is the value of U? As I said, 320 watt per meter square degree Celsius. Okay, we want A. We should calculate this one, 2, and this one because we don't have it. But what do we have? We have m dot for water, 68 kilogram per minute. Okay, so actually we can understand Q from this one and put it here, and after that calculate delta Tm has a formula. I will write it for you, and this is will okay, this will be okay, and we can after that calculate A from this formula. Okay, so let's get started. First we want to, as I said, calculate Q, which we had a formula m, as you remember that m dot for water, C for water, and delta T for water. What is m dot? As we can see in the formula, 68 kilogram per minute. What is the heat capacity of water? We know is 4180. 4180. Okay, and delta T. Okay, as you can see in this problem, we should let me should first draw this diagram for counter current flow. If this would second cross section, it is first cross section. Okay, imagine this is hot, TH2, TH1, and this is T cold 1, T cold 2. Okay, okay, what is okay, let me know what is hot. H is for oil and cold for water. Okay, so we can see at the problem water heated from 35 to 75. So this is 35, here 75, and oil oil enters exchanger at 110 degrees Celsius and leave at 75 degrees Celsius. Okay, so it would be 110 and this would be 75 degrees Celsius. Okay, so in this formula we should write, because this is for water, which one of these is water? The bottom one. So we can write 75 minus 35. Okay, the answer will be 189.5 kilowatts. Okay, this is actually kilogram per minute. This is joule per kilogram degree Celsius, and this is degree Celsius. We should change it. Pay attention. The answer will be something like that. Okay, we have Q in this formula. Well, we should calculate delta Tm again. Okay, for calculate delta Tm, we should go to the formula that the book presented. That formula here. Delta Tm equals TH2 minus TC2 minus TH1 minus T cold 1 ln of TH2 minus TC2 divided by TH1 minus TC1. Okay, we should substitute this value to the formula and calculate that. Okay, so let us do that. What is TH2? 110 minus TC2 75. Is that right? Yeah. Okay, minus TH1. What is TH1? 75 degrees Celsius. Doesn't need to write that. Minus TC1. What is TC1? 35. Okay? We should write ln according to this formula. The same at the top of this. Okay, sorry. Let me continue. 110 minus 75 divided by 75 minus 35. Okay, the answer would be 37.44 degrees Celsius. Okay, so we have to evaluate these two parameters we have. So we can use to understand what is A. As you know, A equals Q multiplied by U. Q divided by U and delta Tm. Okay, is it right? Okay, let me substitute that. Let me change the color because it's so clear, obvious. 189 kilowatts divided by U 320 watts and 2 degrees Celsius, and delta Tm, which is 37.44. The answer would be, pay attention, it should multiply by 10 by 1000 for kilowatts. The answer would be 15.82 meters square. Okay, as you can see, as you can see. Oh, okay. Sorry, my answer maybe is wrong. The answer would be 19.53 meters square. Let's check another calculation. I don't know. No, sorry. It was for another example. Yeah, it was right. It was right. Our answer is 15.82 meters square, as you can see in this example, and delta Tm is 77.44 here, and Q would be 189.5 kilowatts. Everything is great. Okay, thank you for watching this solving of example. Take care, have a good one. Bye bye.